All right, let's get straight into it. Today, we're going to absolutely master one of the most important experiments for your AQA GCSE Physics Paper 1, the specific heat capacity practical.
But before we get into the lab stuff, let me ask you a question. Have you ever noticed on a really sunny day how the sand on a beach can be scorching hot, but the sea is still, pretty chilly? They're both getting hit by the exact same sun. Well, the secret behind that is a property called specific heat capacity, and that's exactly what we're going to investigate.
So, here's the plan. We'll kick off with the theory, what this stuff actually is. Then, we'll walk through the practical itself, step by step. After that, we'll crunch the numbers, see how to nail those tricky exam questions, and then finish up with a super quick recap. Pretty much everything you need for RP1 all in one place.
Right then, section 1, what is specific heat capacity? Honestly, if you can get your head around this concept, the rest of the practical just clicks into place.
Okay, so here is the official textbook definition you've got to know. Specific heat capacity, which we call C for short, is the energy you need to raise the temperature of 1 kilogram of a substance by exactly 1 degree Celsius. Every material has a different value, which, is why sand and sea heat up so differently.
And this is the equation that holds it all together. That little triangle, that's the Greek letter delta, and in physics, it just means change in. So the change in thermal energy is equal to the mass times the specific heat capacity times the change in temperature. You have to know this one by heart.
Look, to make this way simpler, just picture a bucket. A material with a really high specific heat capacity like water is like a massive bucket. You can pour loads and loads of energy into it before its temperature really starts to rise. But something with a low specific heat capacity like our metal block, it's like a tiny little bucket. It fills up super fast, meaning its temperature shoots up with just a little bit of energy. Makes sense, right?
Okay, theory's covered. Let's move on and see how we actually do this in the lab. This is your how-to guide for the experiment. So here's all the kit you're going to need. The star of the show is this metal block, usually aluminium, and it's got 2 holes drilled in it. One's for an immersion heater, that's what's going to supply the heat energy, and the other is for a thermometer, so we can measure how hot it gets. The rest of the gear is just for measuring things like mass, time, and the electrical energy we're putting in. Let's walk through the method. First up, pop your metal block on the balance and measure its mass. Easy. Then set everything up. Now here's a top tip. Put a single drop of water into the hole for the thermometer. That helps the heat transfer properly so you get a much better temperature reading. Then you wrap the whole thing in an insulating jacket, jot down the starting temperature, and flick the power on for, say, 10 minutes. While it's on, you need to record the voltage and the current, and finally, you watch the thermometer and record the highest temperature it reaches after you've switched the power off. Okay, the experiment's done. You've got a page full of results. So, what now? Well, now it's time to do some maths and process all that data. Let's imagine these are the results we got. Let's say we used a nice round 1 kilogram block. We ran the heater for 600 seconds, that's just 10 minutes, and we recorded all these numbers for temperature, voltage, and current. Now let's see what we do with them. Okay, first things first. We need to figure out exactly how much energy our heater supplied to the block. Now we know that energy equals power multiplied by time. And you should remember from the electricity topic that power is just voltage times current. So we can stick those two ideas together to get the equation we really need. Energy equals V times I times T. Step 2 is the easy one. We just need to find the change in temperature, our good friend delta T. It's simply the final temperature minus the initial temperature. So for our example, that's a nice clean 10 degrees Celsius rise. And now, for the grand finale, we have to go all the way back to our main equation. Delta E equals mc delta T, but we need to shuffle it around to get C all by itself. With a little bit of algebraic magic, we end up with this. C equals E divided by mass times the temperature change. Time to plug in our numbers. The energy we supplied, well, that's 12 volts times 0.8 amps times 600 seconds, which gives us 5,760 joules. Then we pop that into our rearranged equation. So that's 5,760 divided by 1 kilogram times 10 degrees Celsius. And that gives us a final answer of 576. Now, what about the units? It's joules per kilogram degrees Celsius. Do not forget the units. Right, this next bit is so important. This is where you pick up the marks for the top grades. It's not enough to just do the practical. You have to understand where it can go wrong and how you can make it better. Okay, here's a classic exam question, and it's a bit of a brain teaser, so listen closely. In a real experiment, the value you calculate for C is often higher than the true, scientifically accepted value. So, why? Why would your result be too big? The clue is to think carefully about where all that energy you supplied is actually going. So, the single biggest reason for an inaccurate result is that not all of the electrical energy from the heater actually goes into heating the block. A whole load of it just escapes into the air and the surroundings. That's your number one source of error. To fix this, of course, we use that insulating jacket. Another little problem is making sure the whole block is at the same temperature when you take your final reading. That's why it's so important to wait a little bit for the temperature to peak after you've turned the heater off. And here's a massive tip for your exam. Seriously, I can't stress this enough. Getting those top grades often comes down to being really confident with these multi-step calculations. So please, please always show you're working out. Even if you mess up the final number, you can still get loads of marks just for showing you know the method. Whew. Okay, we have covered a lot of ground there. Let's just boil it all down to the absolute must-know facts that you need for your revision. Here they are, your top 5 takeaways. 1. Know the definition. 2. Know the main equation, delta E equals mcΔT. 3. Remember how to calculate energy from the heater, E equals VIt. 4. Understand that the biggest error is always heat escaping to the surroundings. And 5. The best way to make your result better is to improve the insulation. Get those 5 points locked into your brain and you'll be in a fantastic position. And I'll leave you with this final thought. You'll notice we always call this practical an estimate of the specific heat capacity. Now, based on everything we've talked about with energy loss, why do you think it's pretty much impossible to stop all of the heat from escaping in a normal school science lab? Have a good think about that one. Hope this has been a real help with your revision.